Good morning, aspirant. Hope you all are doing well. Your days are going productive and you are doing excellent in your work. We will understand complete NMR spectroscopy one by one. For this session, three standard books I have referred and I am writing because of the fact that if you want to study more, then you can refer to these books. First one, Pavia, very popular book. Second one, Y. R. Sharma. This is very student friendly and very small book. And most standard book of spectroscopy is William Kemp. Now to understand any spectroscopy, we have to understand what does this means actually. Spectra means light. Scopy means analysis. So in spectroscopy, basically with light we analyze chemical compound. There are three I in any spectroscopy. Incident of light, first light will come. Interaction with matter, I have a chemical compound, that means matter, it will interact with matter, and from here I will get some light also. From there I will interpret. This interpretation is basically spectra. So light wave, in every spectroscopy light wave is used. So light wave has some energy in terms of photons, and these are wave also, so travel like wave. So light are basically particle as well as wave, right? Light wave is basically electromagnetic radiation, we all know. And there are few kinds of electromagnetic radiation: gamma ray, X ray, UV visible, IR, micro, radio. From this to this, lambda wavelength increases. Wavelength increases means frequency decreases. Now, let's read what is written here. Okay. If on a matter, all the six type of rays are implied separately, no doubt all will interact differently with matter, right? As all these have different energy, so every ray has different energy, so they will interact differently. So all this EMR will create a spectroscopic technique. So for every ray we will have different spectroscopy. Now for gamma rays, X-ray energy is very high and this is sufficient for breaking of bond, so this will break bond in a molecule. So this is not suitable for spectroscopy, but from here we can compare bond energy because this is breaking bond. Next, energy is little lower in UV visible. Here, this system does homo-lumo transition. Homo-lumo transition means electronic transition. We can derive molecular orbital theory as we can interpret homo-lumo energy gap. So this is basically electronic spectra. This is spectroscopy corresponding to UV visible is electronic spectra or UV visible spectra. Next, infrared. This is responsible for bond vibration. So from here, the spectroscopy we get vibrational spectra or infrared spectra. From microwave, it is responsible for, it is lower energy. So this just can rotate a bond. This bond, this is responsible for this rotation of this bond. So this spectroscopy called rotational spectroscopy. Now our important wave is radio wave. This is nuclear spin transition. That means in a molecule we have in an atom, in a molecule, in an atom we have nucleus. In nucleus their spin transition occurs for if we apply radio wave. So here in this spectroscopy, in this nuclear magnetic resonance spectroscopy, we will use radio wave. EMR has no need of medium to travel. That means from sun to earth we know there is no medium, but electrolyte approaches from sun to earth. So EMR, electromagnetic radiation, has no need medium to travel. Mechanical waves should have medium to travel. For example, sound wave. Now, for any electromagnetic radiation, what is electromagnetic radiation? There is two component, electronic component and magnetic component. That means one electric field, one magnetic field. Now, these are mutually perpendicular. Actually, there are three component: electric field, magnetic field, and propagation constant. electric field, magnetic field are perpendicular to each other, right? And if electric field in x-axis, magnetic field in y-axis, and it will propagate through z-axis. So all these things, electric field, magnetic field, and propagation constant k, they are mutually perpendicular to each other, and this is the property of electromagnetic wave. And basically, radio wave is also electromagnetic wave, so that's why it will also have this kind of property. Now, our nuclear magnetic resonance. Here, wave used, radio wave. It is absorption spectroscopy. Now, there are two types of spectroscopy. One is absorption, one is emission. Suppose in a molecule, suppose I am giving some radiation. This middle radiation is absorbed by the molecule, and I am getting this too. So this is basically absorption spectroscopy. Now, in another case, what happens? Suppose I am giving some energy to a molecule and this is excited from ground state to excited state. When it will de-excite, then it will release some energy. If we observe this, this is emission spectroscopy. But our NMR spectroscopy is absorption spectroscopy. Next, nuclear spin transition occur by absorbing radio wave. By absorbing radio wave, nuclear spin transition occurs. For example, nucleus in ground state was in this spin, so it will be uh, undergoing transition from ground state to excited state, and spin will be inversed. Now, as this spectroscopy is nuclear magnetic resonance, so every term is important here. So let's first understand what is nucleus. Let's understand in a deeper way. Now, suppose in nucleus we know there is neutron plus proton. By rotation about an axis, charged nucleon generate magnetic field. In physics, in class 12 physics, we have read that any charged particle if moves, then this generate magnetic field. Right hand thumb rule indicates the direction of magnetic field generated. Right? For example, if a charged particle is moving along this axis, so in this direction it will generate a magnetic field. Suppose if it is north pole, this will be south pole. As simple as that. So two different type of spin will generate two different type of magnet. Okay. So nucleus can be treated as tiny magnets, as N or S pole is decided by external magnetic field. If A is north south, B will be south north. For example, if this rotates like this and here north, here south pole is induced, then with the opposite spin, it will be south north and vice versa. I hope it's clear. So nucleus, every nucleus can be considered as tiny, very tiny little magnets. I hope it's clear to you. Now, for every spectroscopy, there is some selection rule. Which nucleus will show this kind of transition? Which nucleus will not? Right? Is every nucleus, suppose hydrogen nucleus, helium nucleus, any nucleus, will everyone be NMR active or not? This will be decided by selection rule. Which nuclei is NMR active, which is inactive? This is shorted by I value. I value. What is I value? I is nuclear spin quantum number. I is something called nuclear spin quantum number. In electronic configuration, we know some quantum numbers N, L, M, S, right? For nucleus, this is one quantum number called nuclear spin quantum number. We are categorizing this in two sections based on their values. For one case, it is possible that I equal to 0. Another case, I not equal to 0. When I equal to 0, that means spin absent. Nuclear spin quantum number 0 means spin absent. Absent doesn't mean that there is no spin. Overall, there is no spin. It indicates overall there is no spin. NMR inactive. Spin absent means NMR inactive. Spin present if I not equal to 0 when NMR is active. So if spin is present, overall net spin is present. That is NMR active, so I not equal to 0. Now, if I have given some nucleus, how will you understand that which nucleus is NMR active, which is nuclear NMR inactive? If atomic number and mass number both even number, we know even number, odd number. Even number means 2, 4, 6, 8. Odd number means 1, 3, 5. If atomic number and mass number both are even, atomic number, mass number means if any element I represent with A, then this is atomic number and this is mass number. So if atomic number, mass number both are even number, then I equal to 0. Now, if atomic number and mass number, at least one is odd, at least one, or both, right? This can be if either this odd or both odd. All this case will have I not equal to 0. That means NMR active. And this thing was found after observing this type of nucleus. So this conclusion has been derived by observing nucleus. Okay. Now let's see the cases. If atomic number is even, mass number is even, for example 6C12, atomic number is 6, mass number is 12, both are even, 8 or 16. For this case, we know I equal to 0. Now for other cases, I will be not equal to 0. Okay. For example, if atomic number is odd, mass number is even, in that case, I value will be n. That means 1, 2, 3, 4 like this. Sorry, 1, 3, 5 like this. If mass number is odd, whatever atomic number be at mass odd or even, then I value will be n by 2. That means half, 3 by 2, 5 by 2 like this. I hope you have understood it. Okay. Here 2 will also be there, right? 2, 4, 5. Okay. So for this case, n value will be half, 3 by 2, 5 by 2. For here, for this case, n value will be 1, 2, 3. And our proton NMR. So mostly discussion we will be having for 1H1 proton NMR, because most of the organic compounds have maximum protons in it. For example, benzene C6H6. For example, ethane C2H6. So in organic compounds, generally number of protons are pretty much present. That's why we are using proton spectra in great detail. So for different type of nuclei, now you can tell me how the values of I look like. So if I equal to 0, that means NMR inactive. I not equal to 0 means NMR active. Okay. In how many way nucleus can rotate? That is spin state of a nucleus. Now, this nucleus can rotate. In how many ways? How many ways it can rotate? This is being told by something called S equal to 2I plus 1. This is basically spin multiplicity. Now, let's see for 1H1 for protium, I equal to half. 13,6 I equal to half. But for nitrogen, I equal to 1. Let's see for hydrogen. Spin multiplicity for 1H1 will be 2. How it will be 2? Put half in place of I, then 2 into half plus 1, that will be 2. So S value will be 2. That means it will have 2 state. It will split into 2 state. This type of system gives sharp signal. For this one also same 2 state. Ground state is called alpha state and excited state is called beta state. Now for nitrogen, if you put 1 in place of I, then S value will be 3. So that means it will have 3 states. And for these 3 states, we will have 2 transitions. And this type of system is called, this type of signal is called quadrupolar signal, that is not so much sharp. So basically we study this type of nuclei because we get sharp signal. Now here I have written right hand thumb rule. This is basically right hand thumb rule. If you don't understand or if you forgot that, just Google it or search in YouTube, you will get to know. Now, shape of nucleus. Do you know that shape of nucleus is not spherical always? For those nucleus in which I value is half, these nucleus are called non-quadrupolar nuclei. This type of nuclei is spherical. If I value is greater than half, then these nucleus are called quadrupole nuclei. This nucleus is shape is ellipsoid, and for its ellipsoid shape, so many orientations are possible. Okay, for I equal to 3 by 2, tell me for I equal to 3 by 2, what will be A's value? 3 plus 1, 4. So 4 type of orientation is possible like this. Okay. Every moving charge particle has its own magnetic field. So this statement is the basic actually principle for NMR spectroscopy. Now I have written some popular examples of I values for some popular nuclei. You can read it. Okay. Now our major discussion starts. Proton magnetic resonance. I will start it from next class. Till then, have a nice day. Bye bye.